All right, welcome back to another episode of Science with Surback. In this particular video, what we're going to be talking about, one of my favorites here, is sections 16.4 and 16.5, and the objectives for these particular sections is objective number 1, define the pH and calculate pH from a knowledge of the concentration of H plus ions or OH minus ions, and perform the reverse operations. The second objective is this. You should be able to identify the common strong acids and bases and be able to calculate the pHs of their aqueous solutions given their concentrations. So we start out here with the pH scale. And so the pH scale is defined as a method to express the H3O plus concentration, which we're going to call hydronium, in an aqueous solution that uses a logarithmic expression. So let me pause and write that down. All right, so there is that definition right there. And just to clarify, this is the concentration of what we call hydronium ions. And then we can also express this in the concentration of just saying H plus. So H plus and H3O plus, those things mean the same thing. So don't get confused if you see those two terms. Now, that's a great definition here, but for me, I need a formula. And we have a formula to be able to utilize the pH scale. And that formula is the pH is equal to the negative log of the concentration of H3O plus. And that H3O plus we call hydronium. Now, the log scales. I'm not a math teacher, but I do want you to have a little knowledge of this. If we change the H3O plus, the concentration of H3O plus by 10, we change the pH by 1. So let me write that down. Change in the concentration of hydronium ions by 10 equals change in pH of 1. So going through this and determining what the pH scale actually is, or associating values with this, we have 3 scenarios. The first one is going to be a neutral solution of an acid or a base. And in a neutral solution, what we have is this. The concentration of H3O plus is equal to the concentration of OH minus. Now, if we go back one step further and we say, hey, remember what in a neutral solution, that KW stuff, what H3O plus was? Well, if you remember that, the value for H3O plus is 1 times 10 to the negative 7th. And so if I plug that into my pH solution or pH formula that I just gave you up here, I can show you here that this is the negative log of 1 times 10 to the negative 7th. And if I do that, I get a value of 7. So the exact value for a neutral pH is exactly 7. Now, if a solution is acidic, what happens is this. Big picture, we get the concentration of H3O plus to be greater than the concentration of OH minus. And now, I'm not going to associate a specific number here, but typically what you'll have is a pH that is less than 7. So it's 7 or below, or I should say below 7. Our third and final option in terms of our range of our pH is a basic solution. Now in this case here, our hydroxide ions are in greater concentration than that of our hydronium ions. And so again, I'm not going to associate a specific number, but I'm just going to say for a basic solution, the pH is, not less than, the pH is more than 7. So 7.01 or greater. Now typically what you'll see this range is 0 to 14. And that's not necessarily wrong, but you can get negative pHs and you can get pHs above 14. So don't look at that as a constraint. Look at it as it's kind of a basis around that 7, and you'll see why we have that here in a second. But it can be less than 0 in the case of an acidic solution, and it can be more than 14. Just remember that. These things are really important. So to be able to calculate the pH, you already saw me calculate the pH of a neutral solution. So all we need to do is take the amount of hydronium or H plus ions and plug it into our formula. So our pH is equal to the negative log of our H plus or H3O plus. Remember, those things can be interchanged. So the pH in this solution is equal to the negative log of 1 times 10 to the negative 12. So again, if I plug that into my calculator here, I get negative log of 1 times 10 to the negative 12. I press enter, and I get a pH of exactly 12. And so we can do the same thing for this problem down here. And so we have a pH is equal to the negative log of the H plus concentration. And so all I need to do is insert what are the values for H plus. So the pH for my H plus is negative log equals 5.6 times 10 to the negative 6. Again, all I need to do is I need to plug that into my calculator. So negative log times the concentration of 5.6 times 10 to the negative 6. I press enter, and I'm going to round to 2 total digits. So I'm going to round to, in this case, 5.3. So our pH of this solution equals 5.3. Now, this solution is acidic because 5.3 is less than 7. So this is acidic. Up here, this pH is 12. It's more than 7, so it's basic. All right, so now that we have a basic understanding of the pH, we can move on to the pOH. So pOH, it's going to look really similar to pH. The only difference is it's the amount of hydroxide, the concentration of hydroxide expressed in that logarithmic expression. So let me write the exact definition down, and then we'll get back to notes. All right, so there is that written definition. And again, I like to see a formula. I like to be able to crunch some numbers. And so the formula looks very, very similar, except we get the pOH equal to the negative log of the concentration of OH minus. Now, hydroxide. We haven't really talked about hydroxide. But when we get into, or if we remember the stuff from KW, it will make sense why we need that pOH or why we're able to do these things. And that really is the next thing here. How do we relate this pOH to pH? Well, the answer lies in looking at KW. If you remember from the last set of notes, KW is equal to the concentration of H3O plus, hydronium, times the concentration of OH minus. Now, instead of putting KW, I'm going to insert the exact value, which if you remember from the last video, it is 1 times 10 to the negative 14th equals the concentration of H3O plus times the concentration of OH minus. Now what I'm going to do here is I'm going to multiply both sides by the negative log. So I'm going to multiply by the negative log on both sides. And so run out of room here down below. But when I do this, instead of putting just the negative log of that number, let's go ahead, let's put that into a calculation. So we get negative log of 1 times 10 to the negative 14th, close the parenthesis, and we get a value of exactly 14. So 14 is going to equal the negative log of H3O plus times the negative log of OH minus. Now, what I'm going to do here is this. I'm going to leave 14 out and about, but what I have is this, the negative log of H3O plus. This looks really familiar, and because this is what is equal to the pH. So instead of putting log of H3O plus, I'm going to put pH, because those things can be interchangeable. They are substituted for each other if you're looking for a math term there. Now, this times a logarithm. I realize not everybody has a background in in logarithms, but a log times a log is just another way that we can put a plus sign. So instead of putting negative log of OH minus, you can see up here, this means the same thing or set equal to the POH. So our relation between pH and POH is this right here that I just boxed in. And so 14, again, like I said, the numbers sometimes are misunderstood of not having a pH less than 0 or not having a pH more than 15. That's because we kind of get these constraints from this value right here. It is possible to have a negative pH or a pH more than 15. Just keep that in the back of your mind. So we want to calculate the H plus, the concentration of H plus with a given POH of 10.24. So the first thing that I'm going to here is equal plus equals, we don't know the concentration of pH, plus 10.24. Now to get pH by itself, all we need to do is take each side and subtract 10.2 from it. So if we take, in our calculators here, 14 minus 10.24, we obtain a pH of 3.76. So our pH is 3.76. And now this does not answer the question. We want to know what is the concentration of H plus. So what we do here, our pH, remember, is equal to the negative log of the concentration of H plus. So in this case here, our pH, we just found out, was 3.76 equals to the negative log of H plus. Now we have a dilemma. We got to get rid of this log. But before we do that, I'm going to concentrate on this negative sign. So what I'm going to do, I'm going to divide each side by -1. And so this gives me negative 3.76 equal to log of H plus. Now, we have to get rid of the log. So if you look on your calculator, we're going to take the inverse of log, which, whoop, got it too close. The inverse of log is this times 10 button. So all I'm going to do is take times 10 to the root, so inverse times the log, which will just get rid of itself or cancel out. And then I'm going to do inverse log, which is 10 to the power. So 10 to the power, that's what I have in my calculator, to negative 3.76. Negative 3.76. I press enter, and I get some decimals here, so I'm going to change it to our scientific, and I get a value. I'm going to round to 2 decimals, so I get a value of 1.74 times 10 to the negative 4th big M for my concentration of H plus. So that's where our relation between POH and pH is really helpful. All right, so now we can get really into the weeds, and this is, again, some of my favorite parts of really chemistry in general, and we can talk about the how we actually do this in the field or how we do it in a lab environment. So a pH meter. These things can measure pH because they consist of a pair of electrodes connected to a meter that measures small voltage. So let me pause and let me write that definition down. All right, so there is that definition of what a pH meter is. And they're really nice because they give you an exact value of whatever the pH is of a particular solution. However, they must be calibrated often. And what I mean by often, typically what they say on our pH meters is once a month they need to be calibrated and placed into a particular pH solution. If they're not, that electrode here won't perform as expected, and it will need to be either reset or if you dry it out too much, it may be unuseful. So these are nice because they give you an exact pH value. But we have to remember, we have to take care of these. And in our class here, we only use them, the pH stuff, about once a year. So we have to be careful when we use them if they are calibrated. A better way for us in this class is to use pH indicators. Now, pH indicators are going to consist of a colored substance that indicates a solution's pH. Now, these things are really nice, the pH indicators, because they are particular to usually a certain pH range. And the other thing with this is they're a chemical. So we don't have to worry about that calibration process that we dealt with the pH meters. So what they do in details here is they give an exact range of pH where a solution will turn a particular color. So one example, the best way to go through this is an example, and the best way to do it is through a lab experiment. The best example here is the indicator that's called phenolphthalein, and we've used this in class before, whether it was a demonstration or a lab. And phenolphthalein, there we go, indicator. What it does is it will have a color shift from clear to pink in a pH range of about 8 to 9. So it's really helpful here in what we call strong acid, strong base titrations. And when we get to titrations here in a couple sections, this will make sense. Again, these two things, it's nice to know, well, how do we get pH? And it's because of these either A indicators, which are really helpful, and I like these a lot better, or through these meters. So they're actually able to be tabulated in our lab. All right, so moving on here. Now we can get into the real details. We start out with strong acids and strong bases, or we finish up with strong acids and strong bases. And so strong acids and strong bases, they are just strong electrolytes that completely dissociate in solution. That's our big overall definition. So let me write that down and we'll go over an example. All right, so that's a really broad definition of a strong acid. The best way to see this is actually in an example equation. So a strong acid, I'm just going to take nitric acid, a strong acid, nitric here, is going to be combined with water. And what happens is this. notice how there's no equilibrium here. What happens is all of the H's from nitric acid get donated to water to form hydronium or H3O plus, and as the H plus dumps off or gets donated there, it becomes that nitrate ion. So in detail here, all H pluses from HNO3 are donated to H2O. So this keyword right here, all is saying, hey, this is a complete dissociation. So all of this breaks apart and that H plus is donated to H2O. Now, there are 7 strong acids, and you'll need to memorize this, but the 7 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, which we just dealt with, chloric acid, perchloric acid, and the final one is sulfuric acid. Now, it is important to memorize this. You need to know these 7. It is really crucial to be successful in the acid and base unit. Now, let's go to an example here. We want to know what is the pH of a 0.04 molar solution of perchloric acid. So again, the first part, just like we've done the past couple units, start out with a chemical reaction. So we have a perchloric acid. It is placed in water, and again, it completely dissociates because it's a strong acid, and we always check the list there. So what happens is we're left with H3O plus, and we're left with the perchlorate ion. Now, in detail here, we started out with 0.040 molar of HClO4. What that means for us, because all of this breaks apart, that means over here, underneath our H3O plus, we have a value of 0.040 molar H3O plus. So because we get a complete dissociation, the molarity of the strong acid solution is equal to the molarity of our H3O plus. Well, from our formula, if we remember here, our pH formula is equal to the negative log of H3O plus. So we can calculate the pH by just plugging in the concentration of this 0.04 molar solution of H3O. So if we do this, we plug this into our calculator. We say we need the negative log of 0.04. We get this, and I'm going to round to 1 decimal there. We get a pH of 1.4. Now, this pH is way less than 7. It is a strong acid, so it makes sense that it's a really low pH. What we can do now is a very similar type of scenario with strong bases. Now, we start out strong bases with a very generic definition, just like we did for strong acids, and that is this. Our strong bases are strong electrolytes that completely dissociate in solution. Now, this is the exact same definition I just wrote down, so it's not really helpful, but again, the best way to see this is through an example. And our example that we have is if we take sodium hydroxide, NaOH, that's an N, we have this occur? So NaOH, it's going to be an aqueous solution. So it's already dissolved in water. What happens here is this. This thing completely breaks apart to Na plus ions plus our OH minus ions. Now, how do we know if we have a strong base? Well, by definition, our strong bases are going to consist of alkali hydroxides or heavy metal alkaline hydroxides. Now, this is fine and dandy. If you have the groups of the periodic table memorized, that's great, but I like to see a list. So our alkali, and I'm going to put this in quotations, our alkali hydroxides that qualify to be a strong base, are as follows. We have lithium hydroxide, we have sodium hydroxide, we have potassium hydroxide, we have rubidium hydroxide, we have cesium hydroxide, and you probably won't see this very often, but we also do have francium hydroxide. Now, those are all of the alkali hydroxides in group number 1 of the periodic table. And so on the other side here, these things, heavy metal alkaline hydroxides. And I'm running out of room, so I'm going to leave it off. But what counts as a heavy metal alkaline is this. We start out here with magnesium. Magnesium is considered heavy metal. And so we get MgOH2. We get calcium hydroxide, which is CaOH2. We get strontium hydroxide, which is SrOH2. And we get barium and rubidium hydroxide as well. Now, it's important here that radium hydroxide. It's important here that you notice this has 2. So this will actually double our concentration of OH in a strong base solution. So remember that if you ever do some problems associated with this. All right, so let's go through an example. We want to know the pH, not pOH, of a 0.02, and this is supposed to say 0.02 molar solution of NaOH. So again, we've already done this equation. NaOH, it is dissolved in water. It's an aqueous solution, and it breaks down to Na plus OH minus. All right, so now what we have going on is this. Again, we have 0.028 molar solution of NaOH. This stuff right here, it breaks down completely. So what that means is that under our OH column here, we have 0.028 molar of OH. Well, if we know our concentration of OH, we can find the pOH, which is the negative log of the concentration of OH minus. And so all we have to do is plug this value of 0.028 into our equation. So our pOH is equal to the negative log of 0.028 molar solution. So I go ahead, I plug this number, negative log of 0.028, and I press enter. And what I'm going to do, I'm going to round that to 2 digits because I only have 2 significant digits here. And so I get a P, and this is important, pOH of 1.6. Now the problem wanted pH, and that's a more common thing that will be used. So we set this equal to 14 equals our pH plus our pOH, which we know. And so 14 equals our pH plus 1.6. So we subtract 1.6 from each side, and our pH down here at the bottom, our pH, once we go through that, we take 14 minus 1.6, and we obtain our pH value of 12.4. Now, this should make sense because a basic solution is over 7 or greater. This is much greater than 7. All right, so that's everything in sections 4 and 5. I hope you've enjoyed another episode of Science with Surbeck. This is some of my favorite stuff here, talking about acids and bases. So, as always, remember to subscribe.